So, welcome back to the lecture number 5 of the MCTE 512 Artificial Neural Networks and Machine Learning for Engineers. This is the start of our first lecture for the long test 2. So, the long test 2, if we finish it, I think we'll have the long test 2 around 26th of November. Okay. And that means that you have, I'm targeting to finish it, to have the long test 2 in 26th of November. And that means that we will have the last lecture sometime in the week. Now is November. That's why I'm trying to push, because we only barely have how many weeks? So including this week is 1, 2, 3, 4. So I have 4 weeks to finish the lectures. So 4 weeks, but then because I'm using the lab for the lecture also, so that means I have around 7. That's much earlier. Okay, so my target, please note that my target for the long test 2 is around 26th of November. Yes. Okay. So that we finish early. So because they changed the calendar, that was my original. When they changed the calendar, I didn't. Now they have 2 more weeks. It's supposed to be the last week already during that time. Second to the last week, because the last week I don't want to lecture anymore in the last week because everyone is scrambling. If you look at, okay, I will show you the original so that you will know that this is how I program. Okay, my lecture. Let me stop it. Okay. Okay. Now let me share my screen. Okay. So this is the lecture number 5, naive Bayes. So we go back to some review to review some of the topics that we have discussed so far. So we know that for polynomial regression, we want to estimate a function based on the data that is given. Okay, and our estimate is a polynomial function where we will solve for the coefficients of that polynomial according to the degree that we want to do the estimation. Okay, and our measure of how accurate our estimate is based on the error term. And that error term, we'll try to, in this class, we use gradient descent method in order to look for the optimal values of the weights based on the gradient of the error. Okay, that one is well understood. Next, we went to the next topic was decision trees. In this case, again, there is some inputs. Again, that is a function. Our function before in the polynomial, it's in the polynomial regression was a function with some input parameters, and then we look for the weights. In this case here, the inputs is the same thing. You have certain inputs and a function, a decision tree function that will give us a decision, okay, of whether a yes or no answer. And then the question is, how do we create the function? So the function is similar to a tree. So in the structure is similar to a tree. In fact, it is like an inverted tree where your stump is the first layer and your leaves are the last layers. Okay, and then how do we construct the tree? It is by these equations of information gain. The information gain will help us decide on which will be the layer that we will use, and that layer is based on how much information we are going to get. So we want to maximize the information gain. Okay, so if the information gain is 0 or is constant or 1 or certain values that it's not anymore, that means that you won't, it's not anymore that useful to proceed. Okay, so but the information the information gain is big for a certain layer, then we choose that as our preferred layer for constructing our decision tree. And so we have the entropy, the dependent, this is the absolute entropy and the dependent entropy that will help us compute the information gain. Okay, so we have this one. And then now we have the Bayes rule. The third function that we did was Bayes rule. So in Bayes rule, this is the equation. And we are saying that we can take the probability of an event y based on a given event x. Okay, and then this is how the formulation of Bayes rule is. And so this is the given, and this is history, or this is data that is given. So for example, an event y, what is the probability that event y is the probability that event y will happen given event x, such that it is based on the history of the x, the event of x given the y from history. For example, we are saying that the record of people with certain sickness. Okay, if a person has a cancer, then he has most likely has certain symptoms. Okay, then given cancer, given that the case of the cancer divided by the probability of the symptoms. Now, if indeed you have the symptoms, okay, if the X is a symptom, indeed, if you have the symptoms, now what is the probability that you have a cancer? Okay, so yeah, it's quite scary, but that's how it is. It is based on the probability of people with cancer having that particular symptom. Okay, so that's how and then when somebody has that symptom, for example, for COVID, if you have a symptom for COVID, okay, what is the probability that in fact you really have COVID? Okay, and we based on those information of people with COVID and has symptoms. Okay, so now instead of doing the full Bayes rule, we're going to consider an estimate of Bayes rule, and we call it naive Bayes. Okay, so let's start. Naive Bayes is just the estimate of Bayes rule. So from the keyword naive, meaning shy, so it's not the full, like when you smile naively, you don't smile fully. You know, when is this a lady in the class here? When ladies, when ladies somehow they like you, but they don't want to show that they like you, they will naively, and they're too shy to show, they will naively smile. Yeah, so that's how it is. So they don't, so that to conceal because for them it's not nice to show. So now it's the same thing. You don't show the whole, you don't use the whole smile, you don't use the whole formula, but you only use part of it, and given certain assumptions, and we say that at some point it is good enough. Okay, that's why naive Bayes is used by many examples, or many cases. Okay, in this case, let's see, for example, this is the naive Bayes classifier of alligators versus crocodiles. Okay, so especially for us in Asia, we don't, everything for us are crocodiles. We don't have any, we don't say alligators. But alligators are normally, I think they're smaller crocodiles than crocodiles are big crocodiles. Okay, and in this case, like this, in this example, they're huge and the mouth are bigger. So in the alligators, they're smaller and the mouth is more pointed. So here we say that, they say that for alligators, the mouth, the mouth is smaller, this is the dimension of the mouth, one, or I don't know what is the unit here, maybe inches, maybe 3. No, it should be long. It cannot be 3 feet. It cannot be. Or maybe the width, maybe the width like that, not the length from this one, maybe the width. So the width is around 3 inches here in the front, or 1 inch is small. I don't know what's the unit here, but anyway, some smaller size of a mouth, the alligators, and then the crocodiles have much bigger size of the mouth. And also in terms of body length, the alligators are smaller and the crocodiles are bigger. So if you plot this X and Y, the mouth size and the length, the cluster of the alligators will be here on this side, smaller mouth and smaller body length compared to crocodiles with bigger mouth and bigger body length. Okay, so for example, for us in Asia, Asian people, Asian guys compared to, for example, to European or African guys, they're much bigger than us. So normally we're here smaller in size and body length and shorter compared to other races. So in this case here, we have a naive Bayes classifier. So the same thing, we plot, we get more information and we plot the data. And we say that in terms of body length, we can have, in this case here, based on the number of observations. And here you see that there's like a Gaussian distribution of the size of the body length, somewhere between around 8. Let's say that this is 8 feet. This is 8 feet. So 8 feet, you have the average size of the alligator. That means there are more and more alligators of that particular size. While, I mean, this is crocodile. While for the alligators, the average size is around 4 feet. Okay. So now we say that if we plot the Gaussian distribution in terms of the body length, then this is how it can look like. Actually, we can do the same thing for the mouth size. The average mouth size probably is around 2 for the alligators. Again, we don't know what the unit is. And then here, for the crocodiles, the average size is around 8. Yeah. So yes, there will be another Gaussian distribution here for the mouth size, another Gaussian distribution here for the mouth size of the alligator, of the crocodile, and this one for the alligator. Now, so we can summarize this into two distributions. One is for the crocodile, which is the red, and the other one is for the alligator. So suppose we wish to classify a new animal. Okay, there is a new animal that we just found, and it has body length of 3 units. So how can we classify it? So we are only saying, we are only given that it is a body length of 3 units. Okay, we don't know anything about the mouth size. So one way to do is, given the distributions that feature we can analyze which class it is more probable. It's a crocodile or an alligator. So we say the probability of class CJ, where CJ, whether it's crocodile or alligator, given that we observe D. D, we observe the body length. So this is like this one. I think this is in Australia, where so many wildlife will come knocking on your door. Yeah. So here in this case, the alligator is knocking on somebody's door, and we don't know. It looks like an alligator or crocodile. We don't know, and so we only know the measure of the body length. So now, what is the probability that indeed, in fact, it is crocodile or alligator? So if you plot the distribution, we say 3 is around here. So 3 is around there in terms of body length. And here we can say that a large portion is in the alligator, while a smaller portion is in the crocodile. So most likely it is an alligator. But then we can compute it. So the probability of a class crocodile or alligator, given that we observe d of the body length. So given body length 3 and given body length 3, what is probability that is an alligator? And the other one, what is the probability that it is a crocodile? So now this is equal to 10. What is 10 divided by 10 plus 2? So 10 is here. 10 is the number of people in the class, or number of alligators in the class. So here, the maximum is 10. So 10 divided by the total, there are 10 alligators divided by 10 alligators plus 2 crocodile in the body length of 3. So that's 0.83 probability that it is an alligator. In terms of crocodile, the body length, there are 2. Okay, two units or 2 crocodiles in that compared to 10 alligators. So the probability that it is a crocodile is around 0.67%, or this is 16.7%. And so most likely it is that animal was an alligator. Okay, so probability of the body length, for example, we're given another body length 7, another alligator or crocodile, we don't know, came knocking at our door, and we say that we will say whether we want to know whether it's an alligator or crocodile. So the body length is a unit 7. So in the unit 7, the same thing in the distribution, we can say that there are in this class here, there are 9 of the crocodile, that is the red, and there are 3 alligators, that's the blue. So 3 divided by the total, 3 plus 9, and the other case of the crocodile, 9 divided by 12. So it is most likely it is a crocodile. Okay. Then the probability of the class given observed deep, if the body length another alligator or crocodile is 5, then in this case we don't know. So the probability is 50-50. Okay, it could be a crocodile, it could be an alligator. Okay, so the visuals in this case gives an intuition or to describe the Bayes classifier, commonly known as naive Bayes or the shy Bayes, the simple Bayes, or the idiot Bayes. Okay, while going through the math, let's keep in mind that given the unseen instance, unseen instance of a new crocodile or an alligator that we don't know, then we find its probability if it's belonging to one class, okay, and pick where it is most probable. Given that, of course, we find belonging to which class, and we pick the most probable. And given that this is a new unseen instance of the body length, okay. So now, this is the Bayes theorem, which we have already discussed, okay, for many times in the previous meetings. So we say that in this case here, the posterior probability, that means probability of posterior, okay, after a certain event, and given the likelihood and the class prior probability, the before probability, before the event. And so the probability of the particular class, probability of the crocodile, for example, or probability of the alligator. Probability of the crocodile, given that if this is a crocodile, then it has, given a crocodile, then it has a dimension D. That is the database that we know of. And then the predictor of the prior probability, which is the probability of the dimension. So now, given all this information, I don't need to discuss, but then what I want to emphasize is that this is the prior information that we gather before the new information came in. The new information of a dimension, of a new dimension, and now we want to know what is the probability of that being a crocodile and what is the probability of that being an alligator. Okay, so in this case, if you can see, we don't anymore measure the probability of the alligator itself. Okay, well, we consider the probability of the alligator. We consider the probability of all the classes that are given. So in this case, alligator and crocodile. So we compare which one has a higher probability. The one with the higher probability is most likely the one that is the class where that new instance belongs. Okay, so we go to another feature. We say several features. So there are several features of, in this case, 6 persons, male and female: Morgan, Bob, Vincent, Amanda, Reed, Lauren, and Elisa. Okay, so they are over 6 feet. Okay, I think most guys will be over 6 feet. Elisa is also 6 feet and more. So we cannot really say, we cannot tell. Okay, so the eye color, we don't know. I mean, anyone can have different eye colors. Lauren must be, you know, most, if you are red-headed, I think most likely you have a blue eye. Oh, Reed has blue eye. Their eye is purple. Oh, I didn't know somebody has a purple eye. Anyway, so the hairstyle is long and short, and the sex is male, female. So there is, we don't know, there's a random distribution of the sex. Okay, so given all this information, we want to know if there's somebody with a particular sex. Is it over 6 feet, and what is the color of the eye, what is the hairstyle, and what is the sex? Is it most likely, is it Morgan or Vincent or Amanda? Okay, so in this case here, we have, we assume all features are independent. This is the class. These are the things that we need to consider in the naive-Bayes classification. So we are more interested in, particularly, we should be interested in the dependent probability of instances or features. And we assume that each feature is independent of each other. Okay, so for example, here there are features, okay, of xi. So in this case, the features are here. Okay, 6 feet, hairstyle, and sex. Okay, that's a feature. Now we have several features. Okay, given a particular y, or given a particular known information, we set given that this is Amanda, for example, Amanda, and he has all these features. Okay, so feature 1 of Amanda, feature 2 of Amanda, feature 1 given Amanda, feature 2 given Amanda. You know this symbol? You multiply, yeah, it's like a summation. So in this case, you multiply the product of each feature of the eye color given that is Amanda, of the height given that is Amanda, of the hair style given that is Amanda, of the sex given that it is Amanda. Okay, so those are, we multiply. So then we take the overall probability. And the thing that we need to assume here is that in each feature is independent of each other. Okay, they have, so in this case here, mathematically, it is very important because we can separate them, okay, independently. So now, okay, the probability, we can write the probability in the sense that you have a class CJ, for example, and then you have the instance of D, where you can have D1, D2, and D3. This is the instance, how they call it. Probability of the class CJ and the instance of D. So for example, you have instances or features of D1, D2, D3, up to Dn. Several features for a class CJ. Okay, so you can write this. This is the naive Bayes classifier. I mean, this is the probability of all the features given the y. But because our assumption that all the features are independent of each other, we can write it like this. And the way to prove it is that here, if you take the probability, if you write this out mathematically, okay, then we consider each instance or each feature, we say D1 given all the rest of the other features plus the class, multiplied by another feature D2. Okay, we disregard D1 already because we take the probability of D1 in the first term. On the second term, we take the probability of D2 given all the other features multiplied by probability of D3 given all the other features until probability of Dn given all the other features. This is how this is being, this dependent probability or relative probability mathematically can be expressed in this one separately. So each feature or instance with respect to the rest of the other features and class can be written out like this. So that here you have all the features given that particular class. In the other case here, we can modify the equation to say that each feature has this is dependent on the rest of the other classes, on the rest of the other features plus the class, and we can rewrite it like this. And because we say that each class, or sorry, and because we say that each feature is independent of the rest of all the other features, and then we can say that we can remove the dependency here, so we can remain only with that class. So we can rewrite this as D1 dependent on the class, D2 dependent on the class, and D3 dependent on the class. Okay, so this part here of rewriting is the chain rule of probability dependence. We just rewrite out the chain rule of probability dependence. And then here in the third row, we are saying that because all the other features are independent of each other, then we can remove them from the dependency, and now we can only remain with this, such that each feature is dependent only on the class type. Okay, so this is the basic equation of the naive Bayes classifier. So we are saying that there are many other features, but each feature is independent of each other, and it's only dependent on the given class. Understand? So in this is the equation that we are dealing with in terms of naive Bayes classifier. Any questions? So if you take a visual representation, for example, okay. So in this case, each class implies there's one class and there are certain features. So the first feature is okay. So the probability D1 given a class of CJ. So the sex, I don't know which one is the class here. Okay. So given the class that it is a male, okay, given the class that is a male and it is over 6 feet, okay, so it is a male person, and then it is given that it is over 6 feet, and so the probability is 8%. Okay, I mean 80%. And given that it's a male person, and then it has, okay, it's less than 6 feet, probability is 20%. Okay, so for female, so in this case here, probability, given that the class is a male, so it has a higher probability that it is over 6 feet. Given the class it is female, the probability that it is higher than 6 feet is small. Most of them are lower than 6 feet. Okay, so that's that one. Okay, so in this case here, in the table, again, we say given that it is male, okay, and then the eye color is brown, 67%. Most of them has brown eye color, and then for blue is 33%. Okay, so next. Okay, so for female, in this case, the eye color, they're almost 50-50. Half of them are brown and half of them are blue. Okay, 45 and 55. So next, again, male and female, most likely the short hair. Which one? In this case here, there are 3 types: hair, none, bald. Okay, and the short and long. So most of them have short hair. Okay, 80%. And for female, there's very small percentage of being bald compared to the male. And in this case, the short is also very small percent, and most of them have long hair. Okay. So naive Bayes is not sensitive to irrelevant features. So what are the irrelevant features here? So for instance, we will try, if we are trying to classify a person's sex, okay, based on the set features, including the eye color, which is irrelevant to gender. So in this case, the eye color can be irrelevant to to gender, but here in the male, it is giving that the brown is higher than blue. But anyway, so we say that, for instance, if we try to classify a person's sex, okay, given the set of features that included eye color, so we say that what is the probability that it is read, that person is read given the following classification, okay, whether he's male or female, okay. So now we take the probability of all the other features. So we given blue that it is male and female, wears makeup, male and female, and so on, okay. And so given all the features of male, of female, in this case of female, and given all the eye colors, we multiply everything, okay. And given that it is male, we multiply everything, eye color, makeup, and so on. And we say here that in this case, they are identical. I guess it's not, this is just a hypothetical number. But in this case, if the eye color is almost identical, then this one becomes not significant, okay? So what happens here? So what is the thing that he's saying here? Yeah, it's saying here that naive Bayes, if some features are almost identical to each other, they become irrelevant. You know why? Because this factor is the same, almost similar to this factor, okay? And any number multiplying on the same factor, okay, you can either remove them to have just one, no effect, because you multiply it with the same number. So any number will multiply the same number, the strength will become the same. That's why you can cancel them. You understand? Mm-hmm. Yeah, what we are saying here is that in this case, the data, it is just a data that is, it is a hypothetical data. But in this case, the data shows that those with blue eyes for male and blue eyes for female does not really matter much. And in this case, naive Bayes takes care of that because they are identical numbers, almost identical numbers. And so in this case here, it doesn't affect so much about the probability of Reed being female or Reed being male. Okay? I hope that's clear. Okay. So now it works in a number of classes, the naive Bayes. Okay, so that's really the idea here of this equation, that there are many classes or many features given a particular class or given a particular event or class CJ. Okay, so that is the idea. So we can have many features based on a particular class or instance. In this case, it says sex here, but it should not be sex, but it should be a class. Crocodile, alligator, and T-Rex, whether they are friendly or not. And then in this case, crocodile, the same instance or the same class, crocodile, alligator, and T-Rex, and then their color. Okay, so we can have all these instances of probability based on the given class of alligator, crocodile, and T-Rex, and all the other features. Okay, we can consider that, and then we multiply everything to get whether when in certain things or in certain instances, given that it is, for example, friendly, and then is it a crocodile? Yeah, or given that it is a crocodile, will it be friendly? Okay, depending on what data is given to us. Okay, now So there are many cases. Okay, I'm giving a lot of examples here to say that in many instances, we can go back to naive. You can also apply naive equations here, the naive rule here, but the naive rule, we only consider in our equation, we only consider a single feature. But here in the naive Bayes, we have many features which we are considering. So in the way that we approach this in the class, we approach the subject matter in the class. And so now let's concentrate on to say there are several features of a person, a borrower. In this case here, Bob wants to borrow money from the bank, and the bank will know. The bank would like to know what is the probability that Bob will default his loan. Default meaning he won't pay his loan. Okay, so that information is very good to the bank, because when the bank give you money, okay, so for certain people with high probability of defaulting, of high probability of not paying, of not finishing the loan in full, if not fully paying the loan back, then and the bank, in some cases, would still like to give you the opportunity of borrowing from it, but then sometimes they give you higher interest rate because of your higher risk of not paying back. But for people with high probability of paying back, then the interest will become low. That's why in some countries they have what we call a credit history. So based on your credit history, then if you build up your credit history, then the banks will give you less interest rate, because you have proven yourself to pay. You have to pay more diligently. So I guess that's a good information, so that I won't be treated in the same way as a guy who borrows money and then just run away with it. And they should make my life easier, because I have proven myself to be a good borrower. Okay, so now in this case, Bob, is he a homeowner? No, Bob is not a homeowner. Is Bob married? Yes, he's married, and his job experience is 3 years. Okay, so in this data that is gathered throughout all the years of banking, information in the bank, so they create this table. If you're a homeowner, if you are married, marital status, and then your years of job experience, then they plot. They say, will you default? That means you won't. Will you pay back? Will you default, or you stop paying, or no? So no, it said no. That means not defaulting. That means you'll finish the loan. Okay, your homeowner, yes. Okay, he owns the house, is single, 3 years of experience in the job. Okay, so sounds like he's living a good life, right? Not renting and single, all his money is his, so he will not default the loan. Okay, now not a homeowner, okay, married, okay, 4 years in the job, okay, according to the record, also will not default the loan. That means he will pay. He will pay back. So let's look at this one, the one that will default. Not a homeowner, he's renting, he's divorced, so he can go everywhere he wants. No one to hold him back. Years of job experience is 2, okay, and according to the record, according to a previous record, this person didn't pay. Okay, so who else didn't pay? Not a homeowner, married, has 3 years in experience, also didn't pay. Okay, a homeowner, single with 2 years of experience, also didn't pay. It's almost the same as this one, but here still he didn't pay. Okay, so based on those information, we're going to use that to judge whether a new data, a new person that is not included in this data, given this information, not a homeowner, married, and has 3 kids, will he default the loan or not? Okay. So based on the data, okay, here you have, will default the loan, yes, default the loan, or yes, or no, default the loan. It will not default the loan. The Y or the Y output is of yes or no. For the no case, it has 7. So 1, 2, 3, 4, 5, 6, 7. 7 divided by 10. So probability of the no that Bob won't default is 7/10. When you're a homeowner and you're a no, so given that the no and you're a homeowner, okay, you're given that you are no and you're not a homeowner, you'll not default, but not a homeowner. Okay, so you're just renting, but still you're diligent in paying your loan. So what is the percentage of that? So let's find it. So that's no, and then how many? Let's count. For those of the no, there are 7 already. We know this: 1, 2, 3, 4, 5, 6, 7. For all the no's, then we want to know what is the number of those that are not a homeowner. So 1 for the no, 2, 3, and then 4. So that's 4. So 4 divided by 7. Okay, and then for all those no that are married, that won't default but married. Okay, no, married, 1, 2, no, 3, 4. So also 4/7. Okay, for the job experience of 3 years, exactly 3 years. No, job experience 3, or that's 1. No, job experience 3, that's 2. So that's 2/7. So now, what is the probability that Bob will not default? Okay, probability that there's a new data that this guy will not default. Okay, so what is that? We multiply all those probabilities. Probability of the no, okay, probability of the overall output, and then probability of all those other features, or all these other probabilities of the features that are given, given that that person won't default. And so we multiply everything, and we say that the probability is 0.0, I mean, it's 0.065. So probability is 6.5%. What does it mean? It means that no, he won't default, or yes, he will default. Yes, he will default. This is higher probability that he will default. Okay. Okay. So here, this is smaller. Okay. So let's consider this. If now we consider the cases where the cases of people that will default. So in the case of yes, you have 3 yeses out of 10. Okay. Now of the yes of the not a homeowner, no, you have only yes, not a homeowner, 1, 2. Why? It should be 2. Okay. Anyway, that should be 2, because according to this one, is a yes, and a homeowner no. Homeowner no is 1 and 2. Okay. For the marital status, you're yes, but married, there's a 1, so that's 1/3. And yes, but the job experience is 3. Yes, job experience is 3, and then you have 1. So 1/3 times 3/10, which is the overall probability. This is much smaller than this one. I thought this one, the yes will become, the yes is bigger, but in this case, no. The yes is smaller. So now this is the probability that Bob will default. That means he won't pay, but the probability that he will not default is higher. So most likely Bob will not default. That means Bob will pay his any questions? So good. In this case, don't forget that we are only considering this, the naive Bayes classifier of all the features given a certain class. Okay. So in this case here, we're supposed to have classes, a certain class are given a feature. But in the other case, in this one, we don't only consider the class of the no, but also we include the probability, the entire probability. In this case, it's supposed to be like this according to the original description of the naive Bayes, but they include this other factor of the overall probability. That's fine because we also do that to the same other class. So the overall probability of, because in this case, when you're doing naive Bayes, we always compute all the possibilities and compare which probability is higher and which probability is smaller. So we take always the one with the higher probability is the one that will most likely happen. So in this case here, the absolute probability or the overall probability is included. It results in that number with all the other features that are given. The same thing with all the other features that are given, including the overall probability is smaller than the other one. And so we say that most likely Bob will not default. So that means Bob will pay his loan. Okay. But again, bear in mind that this is what we are doing. Okay. Given the class and all the other features, we multiply everything. So now let's go back to this example. Okay. So now in this case, we have symptoms and occupation and the ailment. Ailment is like the sickness. Okay. When you are sneezing, excuse me, and you are a nurse, okay, and you have flu. That is the data. Okay. When you're sneezing and you're a farmer, you have hay fever. Yeah. So when you have a headache and you're a builder, you have flu. Okay. When you have a headache and a teacher, you have concussion. What is concussion? Concussion.
It's when you.
I thought you have, let's say, something in the head. No.
Yeah.
Yes.
Is that the one?
Yes, sir.
Like you hit your head with something, right? Is that the one? Concussion?
Yes.
Yes.
Okay. Okay. Yeah. It's yeah. But well, it's much more severe. I'm just wondering because that's much more severe from the rest of these flu and hay fever. But anyway, so what you're saying here is that if your symptom is you are sneezing and you're a builder, so what do you have? Okay. So you're sneezing and builder here? No. Okay. So it's not included here. So based on this given data, if you're sneezing and you're a builder, most likely what is your ailment or what is your sickness? Okay. So how do we do this? So we apply in this case here, we apply the full Bayes rule. Okay, we can apply the full Bayes rule, and we can also apply the naive Bayes rule that is based on certain things, based on all the probabilities of all the features. But in this case here, let's consider all the features in the case of the full naive Bayes rule. Okay, so given we know that these are the features, okay, that you are a builder and sneezing, and given what is the probability that you have flu. So because this is what is asked. Sneezing and builder, the probability that you have. So in our case, in the case of the right hand side of the equation, we say that flu, based on the history, when you have flu, okay, that given that you are flu, and it means given that you are flu and you are a builder, you are sneezing builder. Okay, the probability, given that you have a flu and you are a sneezing builder, what is that probability multiplied by the probability of the flu divided by the probability of the sneezing builder? Okay, so how do we compute all this? So now let's go back to the data. So maybe on this one. Okay. I should have written this whole thing around here so that it's easier. Okay, never mind. Probability of the flu, write it down. Okay, you have this, we are considering only this data set here. Table. And probability of the flu 1, 2, 3 divided by
6.
3/6. Okay, then probability of flu and sneezing. Why you want the flu and sneezing? Why?
Because the builder is sneezing.
There are several features, and we're saying that the features are independent of each other. Okay, let's just put S here, S and builder. I want to write it down. Sorry, I wanted to write it down the way we have written. Given probability so that we will know how to deal with this one. Probability of sneezing, comma. Okay, so how do we write it down? That we know that features are independent of each other, and so what we can do here is probability of sneezing given flu, probability builder given flu, probability of flu divided by probability, again because they are independent of each other, probability of sneezing, probability. Okay. Let's write out everything. So probability of flu, we know it's 0.5 from the table. Probability of, given that flu and you're sneezing, so given the flu and you're sneezing 1, 2, 3, and sneezing is 1, 2, right? So 2/3. So yeah, this is 2/3. And you are a builder and having flu. So flu again, let's go flu. Because we want to know this one, flu and sneezing and flu that is a builder. So we already know the flu and sneezing. Okay. This probability of the flu is here. Probability of given flu is that one. And probability of builder, flu and is a builder, that one. The next, so probability of sneezing, builder, and flu, that one. Sneezing, builder, and a given flu, and sneezing and builder, we multiply them. So they just multiply that, and we collect this one. So the other at the bottom is probability of sneezing, absolute, and probability of a builder, absolute. We solve this because this is the result that the features are independent of each other. This is equivalent to this. That this equation is equivalent to this. That's why these two are being multiplied. Okay. So now, what? So we know this part. Flu, given flu and sneezing. The next part is given flu and is a builder. So given flu and is a builder, there's one. So there are 3 flus and 1 builder. So that's 1/3. So yeah, this is 1/3. That's 33.33. Okay. So now we multiply this. These two, you multiply it, and that's the result of this part. Okay, 0.22. So this part is 0.2. Okay, probability of flu, we know that already. That's 0.5. Now we know the probability of sneezing. Okay, where is sneezing? So 1, 2, 3. 3 divided by 6. Okay. Probability is 0.5. Probability of the builder. Where's the builder? 1, 2 over 6. So 2 over 6 is 1/3. So this is 0.33. This is 0.165. So now it is just a direct application of these equations. And so we want to know that the sneezing builder, what is the probability of the sneezing builder having a flu? It turns out that the probability is 66%. So most likely he has a flu. Okay, any questions? Okay, the question is, sir, why in this case we are considering all the naive Bayes, okay, equation, including the top part of this part, including the bottom part, but in some cases we only consider this one only. Okay, and in some cases we consider this one. Remember that there was an absolute probability of the yes and the no. This one, see? These are all with the features. And this one is the one with the absolute probability of the output, yes or no, which is in this equation. Okay, let me. Okay, these are understood. Yeah, the values are straight, I think, straightforward. We can clear all of them. Now the question is why? In that case, we are considering everything. Okay, in some cases we consider this. In some cases we consider all of this, and in this case we consider the whole thing. So which one do we apply? Just a question. Okay, it's going to be 1 hour. Let's have a break, and we will answer the question when you come back. Okay, 10 minutes break. There are how many of us? 8 students. Okay, not bad. Okay, see you in 3:20.